Hey, you're hanging with Hussick. Welcome to Organic Chemistry, and this video is going to be about hydrocarbons, in particular, how to identify the different hydrocarbon families, alkane, alkene, and alkyne, how to name hydrocarbons from the picture, from the structural diagram, and how to draw the structural diagrams from the names. So, a few fun facts and details about hydrocarbons in general. So, they are organic compounds. This means that they are organic in origin, and it's like a chemistry term, not a pop culture term or a food-based term. You've probably heard the term organic for foods that are grown without pesticides and certain fertilizers and everything like that. We're not talking about organic in that sense. We're talking about organic in the sense of pure chemistry, which means that they've originated, ultimately, these compounds from the photosynthesis process in plants. So if you think of like what's something that's inorganic, that's something that's carbon-based, but for example, CO2 would be an inorganic compound because that's the form that carbon takes when it's in the air. Okay, so CO2 would not count as an organic compound, and neither would carbonates that you find in rocks or hydrogen carbonates. Those would all be inorganic forms of carbon. But once photosynthesis happens, okay, we can take those inorganic forms of carbon and turn them into organic forms of carbon. And they all start as glucose, but all the derivatives of those that we find in plants and animals and carbon-based compounds that interact in living systems are referred to as organic. Anyhow, you don't necessarily need to know that, but it's a fact that you should learn anyhow. Hydrocarbons in particular, as organic compounds, are commonly used as fuels. Okay, so you think about automobile fuels and just in general, when you think of hydrocarbon fuels, things like propane and methane and butane and octane, these are all fuels that are hydrocarbon fuels. They're non-polar molecules, and that's because of both the bonds that are present, which happen to be polar, but moreover, as you've learned previously, the fact that those polar bonds, those carbon-hydrogen polar bonds, they cancel out due to the symmetry in these molecules. So these molecules are non-polar. That also means that they will only be soluble in other non-polar solvents, or they themselves could be non-polar solvents that might dissolve other non-polars, because like dissolves like. Hydrocarbons are made only of, so if you're following along, we're down here, they're made only of carbon and hydrogen, okay? No other atoms are present in true hydrocarbons. And remember that each carbon wants to make 4 bond pairs. So the nature of carbon in general, it has 4 valence electrons, and a carbon atom wants to have 4 bond pairs to satisfy the octet rule. And in the case of hydrocarbons, that means that we're going to fill out these structures with hydrogens, generally speaking, to make sure that each carbon has 4 bond pairs. So let's have a look. Okay, since we're talking about carbon-based organic compounds, hydrocarbons, we're going to need to name them and draw them, and we need us to learn the system for which we name these compounds and draw the structures of these compounds. And it's something called the IUPAC naming system, the IUPAC naming system. IUPAC stands for the International Union of Pure and Applied Chemistry. So these are basically the chemistry nerds that make the rules about how we name these compounds, and it's meant to be an international system so that no matter what country you're in or no matter what language you speak, we should all have a common understanding as chemists about what that dangerous stuff is in that particular beaker or flask, okay? And so we use a system of prefixes based on the number of carbons that are present. So if we have a 1-carbon compound, we use the prefix meth or methyl. If it's 2, we use eth. If it's 3, we use prop. If it's 4, we use but. If it's 5, we use pent. If it's 6, we use hex. 7 is hept. 8 is oct. 9 is non. And 10 is dec. And the suffix that comes after the prefix is actually based, so what comes next, in other words, is actually based on the type of hydrocarbon or the type of organic compound that it is, okay? And so we'll analyze some of that afterwards, but essentially the main chain, or what we call technically the parent chain, gets this prefix, okay? So overall, we examine what is the parent chain in this compound. Does it have 4 carbons, for example? Then we know it's going to be a bute. Okay, does it have 8 carbons? We know it's going to be an oct. And then we decide the suffix based on which family it's a part of. Okay, so the first and simplest hydrocarbon family are the alkanes. And the alkanes are defined by the fact that all of the carbon-carbon bonds in these compounds are single carbon-carbon bonds, okay? All alkanes have the common or general formula, as you see here, CnH2n plus 2. That means, for example, for this compound below, if you count the carbons and you count the hydrogens, you're going to find out it's got the general formula whoops, let me get the right pen going here. Classic issue for me. C5. And then if that's N, so you're going to make it 2N, which is going to be 10, and you're going to add 2, so it's going to be H12. Count the hydrogens, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, okay? So it has this general formula overall for its, what we would call its molecular formula, okay? If we draw the structure out, it's called, like we've done here, like we've done down here, it's called the structural formula or the structural diagram, okay? And we always give it the suffix ane, so it gets the ane suffix. So if we look at this structure that's circled there, for example, you can see the longest run of carbons in the structure is a 5-carbon run, okay? So because it's got that 5-carbon run, we know it gets the prefix pent, okay? So it gets this pent prefix, it gets the ane suffix because it's an alkane and all the carbon-carbon bonds are single bonds. So the name of this structure would be pentane, okay? Also of note, which you can see right here, all the bond angles in this structure would be 109.5 degrees. And you should remember this from Lewis structures because if you look around each carbon, the shape around each carbon is tetrahedral. Okay, so a couple examples here for naming and drawing hydrocarbon structures, alkane structures. So I might ask you to draw the structure of octane, okay? And you should then come up with something like this, okay? You see that in actuality, since it's oct, that means that the longest run of carbons should be 8. So you'll put 8 carbons in a row, like this right here, 1, 2, 3, 4, 5, 6, 7, 8, right? And then you just fill it out. Ane tells you that each carbon-carbon bond is a single bond, and you make sure every carbon's making 4 bond pairs. Fill the thing out with hydrogen, with hydrogens, and so you know also that the formula, the molecular formula of this is going to be C8 and then H18. It'd be N and then 2N plus 2 for the number of hydrogens, right? In a further example, I might say name the following and show you this structure, and I've highlighted, well, the longest run of carbons in that exclusively carbon-carbon single bonded structure is 4. So we would give the prefix butane. Okay, for prefix but, suffix ane, the name of this would be butane. It's an alkane. Okay, we've looked at basic alkanes. What you can also have in alkanes is you can have substitutions, and you can have what they call branches. So a branch or a substituent is a group that's attached to the parent chain. It gets named before the parent chain, and it's numbered according to what carbon it's attached to. So we give the branches the lowest numbers we possibly can, in the structure of naming. So have a look at this structure below, for example. And what I'd like you to just pause for a second. And what I'm going to ask you to do is identify the longest run or the longest continuous chain of carbons in the compound. Okay, if you did that, you probably found that this indeed was the longest run right here. 1, 2, 3, 4, 5, 6, 7. Okay? What would your other options be? Well, maybe you look this way and say 1, 2, 3, 4, 5, 6. See, that's not the longest. Or maybe you count, you could turn other corners and whatnot, and you might get to 6 a couple different ways. But the longest chain is, in fact, going to be 7. So we know the base name of this is going to be heptane. Let me put this in a color that I want to put it in. Heptane. Okay. Why ane? Remember, because all the carbon-carbon bonds are single bonds, so we know this is an alkane. Okay. So we're working on the basis that this is heptane. I'm going to highlight that so you know that's why we did that prefix. Okay. But this heptane is branched. It has some branches. And the branches, we're going to highlight those. We've got a branch right here, that is a 1 carbon branch. And then we have a branch down here that is a 2 carbon branch. Sorry, I'm going to circle that in red so you can tell the difference. We have a branch down there that's a 2 carbon, okay? So how do we name these branches? Well, when it's a 1 carbon branch, we call it a methyl group, and when it's a 2 carbon branch, we call it an ethyl group. Okay, so we know that this is going to be some kind of an ethyl methyl heptane. Okay, so now we're building an even more complex name, accounting for the branches. We have to note which carbons the branches are coming off of. And I'll show you how we do that. So we number the carbons in the parent chain, and we would number them like this. 1, 2, 3, 4, 5, 6, 7. Okay, so that these branches, the methyl is coming off of carbon 2, so we would call it 2-methyl. And the ethyl is coming off of carbon 4, so we would call it 4-ethyl. Okay, now there are several things to note here. First of all, what if we chose to number the parent chain backwards? And instead of starting with number 1 on the left-hand side, we started with number 1 over here on the right-hand side. Okay, then the numbers for these things would be 1, 2, 3, would be 4, 6 instead of 2, 4. Okay, well, the answer is you never do the larger numbers. Okay, you always use this rule. Use the lowest numbers possible to assign those branches. So we'd always choose 2 and 4 instead of 4 and 6. Okay, second important thing to notice. If you look at the branches, and again, I'll kind of highlight. Here's the ethyl, okay, in red. And then here's the methyl in blue. Now, it was no accident that I wrote them 4-ethyl, 2-methyl, okay? Obviously, I did not go in order of increasing number, but what I did go in order of was the letter that the group starts with. So E comes before M in the alphabet, and so we list the branches alphabetically. So since E comes before M, we write ethyls before methyl. I know it's kind of an annoying rule because methyls are shorter than ethyls, but that's what we do. You'll also notice that we put the YL ending on there. That's because these branches are referred to as alkyl groups. Again, welcome to the extra vocabulary and language of organic chemistry, but they're referred to as alkyl groups, these branches that are all kind of alkane, alkane residue branches. What else do you have to highlight there? Oh yeah, you'll see we used a little stick like this, a little dash. Every interface of number to letter gets a dash, okay? So anywhere you have 4-ethyl, you put a dash between 4 and ethyl. 4-ethyl, 2-methyl, you have a dash between ethyl, 2-methyl, right? And then technically, even though I haven't written it perfectly, this could all be one word, methylheptane. Okay? And that's how you would number that thing and name that thing and draw that thing. Okay, next hydrocarbon family, and we're just going to go through the basic 3 hydrocarbon families, but the second one is called alkenes. Alkenes have the general formula CnH2n, so in other words, the hydrogens are double the number of the carbons. They have at least one carbon-carbon double bond in their structure. And so if you look around the carbon that has the carbon-carbon double bond, it is going to have a 120-degree bond angle, and it's going to be what we would call trigonal planar in its geometry. So a couple quick examples. If you look at the one down here, a 2-carbon alkene. I forgot to mention, but these get the suffix -ene, okay, as opposed to -ane. So we would call this ethene, and that's because it's 2 carbons, right? Parent chain, same old situation, the rules repeat. Parent chain, 2 carbons, eth prefix, ene suffix, because it's an alkene, it has a double bond. This one here, next to it, we would actually call, it's 3 carbons, so it's going to be called, excuse me, gotta find the pen again. There we go. It's going to be called propene, okay? Now, in propene in particular, we don't have to number the double bond because there's really, it doesn't matter if we put it here or if we put it here. Remember, these molecules are like 3-dimensional things. So if we were just to flip it, spin it 180 degrees, you'll see that it's actually the exact same molecule, okay? So that's called propene. Now I'll show you some where you do have to assign the position of the double bond in the molecule and how you do that, and some where there could be more than one double bond, carbon-carbon double bond in the molecule. Okay, so if you check out these two, it's a really interesting comparison. So first of all, let's just have a look at these 2 molecules and realize these are not the same molecule. However, they're both alkenes, because they both have that carbon-carbon double bond, right? Maybe I can highlight that for you so you can see exactly what I'm talking about. There's a carbon-carbon double bond there, and there it is there, okay? But you can see it's not in the same position, right? So if you wrote what we call the molecular formula for this, it would follow the rules for an alkane. It's C4 if you count the carbons. Twice as many hydrogens, it's H8. And same with this one, C4H8. But when they have the same molecular formula, but a different structure, or a different structural formula, then they are what we call isomers, okay? So these are called structural isomers. Okay, and we're going to learn more about dealing with structural isomers in a moment's time, but the point of this is supposed to be to name them. And so they're 4 carbons long, so we know they're going to be bute. They contain a double bond, so we know they're actually going to be called butene, and indeed both of these are butene, okay? But how do we designate or communicate that they're actually different molecules? Well, this one you can see that the carbon double bond is after carbon 2, or in other words, it's between carbon 2 and carbon 3, and that's true no matter how you number those carbons, right? So we call this 2-butene, whereas this one, the carbon-carbon double bond is between carbon 1 and 2, so we actually call this 1-butene. Alternatively, you can refer to these as bute-2-ene or bute-1-ene, or I think, although it may not be standard IUPAC, I think you sometimes also see this called N-butene, like normal butene. I don't know, but At least the first two are correct IUPAC names. And again, follow the rule of you always give that that double bond, and now we might use the appropriate term for it. It's called a functional group. It's something that, a feature of a molecule that defines it as a member of a family. So for an alkene, the functional group is the double bond. You give that double bond the lowest number possible. So you would never call it 4-butene. You would always call it 1-butene, so that you indicated it came off of carbon 1, as opposed to numbering it backwards and saying it came off of carbon 4. It'd be the same structure, but you choose the lowest number. All right, here's one where I didn't draw the structure correct. There we go. I forgot a hydrogen. So here's one here where we've now got actually a branched alkene. So there's a branch coming off, a methyl group. I mean, alternatively, you could identify that as the methyl group if you think about it. It doesn't really matter. We know that the longest run of carbons continuously, and I'm going to highlight it for you, is this one right here, and that it's 5. Okay, so since it's 5, we use the prefix pent. Okay, and so this is a pent, and we see it has a double bond right there. So it's actually pentene, right? What's the position of that double bond? It's on carbon 1, so this is going to be 1-pentene, all right? So we know it's going to be 1-pentene, and we have to indicate that there's a methyl group attached to that pentene. Now, what carbon number is it on? 1, 2, 3, 4. So we're going to call this 4-methyl 1-pentene. That's going to be the name of this thing. Okay. Now you might say to yourself, why did we number it to give the double bond the lowest number, right? Instead of giving the methyl the lowest number. Well, there is another rule layered on here, and you'll get used to it. It seems like a lot of rules, but we give the functional group what we call priority. So the functional group gets priority. God, I'm such an ugly writer here. Good Lord. Clean it up, son. Clean it up. Priority. Functional group gets priority in numbering. Okay, so in other words, it gets the lowest number, even before branches. Okay, so we go ahead and give a high number to a branch if we need to, in order to give that double bond a lower number. By the way, sometimes, even though I would think it's kind of bad form, they'll just call this 4-methyl pentene. Like, they won't give a position for the double bond. And if they do that, you know it's a 1. Okay? If they don't give a position, you basically know, oh, it means it's a 1-pentene or pent-1-ene. Okay, third hydrocarbon family is going to be the alkynes. Okay? Like the alkenes, they're defined by something different happening between the carbons. There's at least one carbon-carbon triple bond. So these have at least one carbon-carbon triple bond in them. Okay? They have the general formula CnH2n-2, because you can fit a few less hydrogens in there when you have that triple bond. What you're going to see with these guys is that the bond angle around the carbon is going to be 180 degrees. Right? And that's because it is linear around any carbon with the carbon-carbon triple bond. Okay? So if we look, and then the suffix is -ine. Okay? So it would be like ethine, propine, etc. Okay? So, for example, structure might be something like this. Fill it all out with hydrogens. Missing one on that carbon there. There we go. So you'll see that this is going to be C3H. Count them up. It's H4. Okay. 2N, would be 6 minus 2 is 4, yeah. So C3H4. And the name of this, you're probably getting used to it by now. Longest run of carbons is 3, so it's prop. And so this is on carbon 1, but really there's only one kind of propyne, so we would just call this propyne. Okay? Same as the others, I won't do a million examples of these, but you could have branches attaching. You need to denote the position of the triple bond by numbering the carbons, give it priority over branches, etc., etc. There's another video where I'll go through some more examples of naming and drawing hydrocarbons, but this is the basic ones for the non-cyclic hydrocarbons. So what about the cyclics? We can throw a slide in here for the cyclics. I want you to know those ones as well. That's where they're basically bonded in a circle or whatever. You know, they're bonded in a continuous, in a loop, okay? So we might throw one in like this. I'm just going to put sticks going to nowhere, and you can imagine they're filled out with hydrogens. It's another little lazy guy trick that I do, but the chemists do in general. Or we can be even lazier and just draw it like this. It's called the skeletal diagram. So if you have 4 carbons bonded in a loop like this, this is, instead of being referred to, so usually if you had 4 in a row, 1, 2, 3, 4, we would refer to this as meth-prop-bute. We would refer to this as butane, right? Well, this is called cyclobutane, okay? So either of these would represent cyclobutane. Again, you could have them substituted, branched. One thing is, if you have the, let's say you have the double bond in the structure, like this, okay? So this would be, and again, I'm going to try and quickly fill out the hydrogens. This would be called cyclopropene. Okay. You want to, if you have to number the carbons for branches, you go ahead and, again, give the lowest number, give the priority to the functional group. So we'll work on some cyclic examples as well. Hopefully you find this helpful and laying the groundwork for naming and drawing hydrocarbons.